of the Digital Twins for Infrastructures and Cities Master Program. So as you may know, we invite from every once or twice a month people from different areas, companies, industry, or research to talk about digital twins for infrastructures and cities. And so today we have the pleasure of having Alexander Popp. So Alexander is a full professor at the University of Bundeswehr Munich, mostly focusing on computer-based simulation. So Alexander is quite known in the community of computational mechanics. He's an expert mostly on numerical methods for contact and high-performance computing. So he's a PhD from Technical University of Munich. And quite recently, I don't know exactly since when, Alexander, maybe you'll tell, but you also started some research activities on digital twin technology and physics-informed machine learning. And since 2022, you're also a vice director of a new institute for the protection of terrestrial infrastructures. So maybe you will speak about that today with people working on different concepts and technologies to improve the resilience of critical infrastructures. So I think it will be the topic of today's talk. So thank you again, Alexander, for being here, and thank you all for attending the conference. I will give you the floor. Thank you.
Thank you very much, Jeremy, and well, thanks to all the organizers for having me. I mean, I find this a very fascinating program, so it's great to hear that something like that exists on the European level, and so I'm very happy to contribute today and to introduce to you maybe some new activities that we started in the last few years in the German research landscape on the main topic of digital twins and also the enabling technologies for critical infrastructure protection. So as Jeremy correctly said, I have kind of a double affiliation at the moment. So I'm professor at the University of the German Federal Armed Forces, so which is quite a special university, but you know, no reason to be scared. I'm not a military guy or something like that. It's just a university that's supposed to educate the future officers of the German Armed Forces. And I'm specializing there on everything related to computational mechanics, as Jeremy correctly said. And taking it from there, in recent years, I built up a second focus of my research, which was revolving around digital twins. And the application case that emerged from this is basically infrastructure modeling and infrastructure monitoring. And so this is where our two fields of research interest basically met recently. And so I'm happy to be here and to talk a little bit today about our activities. So I hope you will find this interesting. So since I'm maybe new and for most of you, I'm going to do a very quick introduction beyond what has just been said. So who are we and who do I represent? So on the one side, as I mentioned, as part of the university, within the university, we've built up also in recent years a research project that is called RISK.twin. So you can already see from this acronym that RISK obviously refers to risk associated with the treatment of infrastructures, and twin refers to the digital twin as the central research theme that we have chosen there. And so it's kind of the deal basically is that we do the fundamental research within our groups at the university. So we have expertise there in the civil engineering department for several sectors of infrastructure, right? Transport infrastructure, but then also in the building industry and also everything related to energy sector, water sector. So all the classical sectors of critical infrastructure with the domain knowledge. And then we have these integrative parts such as simulation, model order reduction, scientific machine learning that try to condense this domain knowledge into tools that can be useful in engineering practice and also in basically infrastructure maintenance and infrastructure monitoring practice. And then, as Jeremy correctly said, about 5 years ago, a new institute was founded within the German Aerospace Center. So at first, this might sound a bit strange because German Aerospace Center sounds like it should focus on aerospace, right? It also still does focus on aerospace, but not exclusively. So the name is kind of a bit outdated now because we're also in the German Aerospace Center have a strong focus on energy research, on transport research, and in recent years on safety and security research. And so this new institute that I have the great pleasure to lead since now 3 years is an institute that focuses entirely on the protection of critical infrastructures. It's called protection of terrestrial infrastructures, meaning that we focus on developing concepts for critical infrastructures at land. So in contrast to critical infrastructure that, of course, also is very important in the maritime sector. So at sea, I mean, in recent years, you've heard many incidents of underwater sea cables and data cables that run, for example, in the Baltic Sea. And so this is kind of the separation that we have chosen here. And this is a research institute that is now growing and where we focus more on the application side of those research. So we really try to transfer also technologies then into industry, to critical infrastructure operators, but also to government agencies for the decision making. And again, there, the digital twin is kind of our central software platform, our central concept, where we try to provide useful services to our customers. So maybe just 1 or 2 words more about the organizational structure of this DLR Institute, because this is really where the main part of this research is now taking place these days. So with digital twins, probably I don't have to explain to you. And if you think about infrastructures, we have to cover a very broad spectrum of research. I think this is one of the main goals, if you want to start from there, why the field is still so heavily developing, because you can't just focus on, I don't know, you can't just focus on structural mechanics modeling, for example, or you can't just focus on traffic modeling, or you can't just focus on sensor technology, but you need all of this. And you need the combination of all of this to really come up with useful tools for practice. So it's a very complex and diverse field, which on the other hand, I mean, you're in an executive master program, which I think is good news for you, because this makes it, of course, attractive to be part of this community and to push this field forward in the next years. So within our group, we've decided to focus on 4 main pillars of our research that already show how diverse this is. So the one that we start with, the foundation, if you wish, in terms of theory and modeling, is called resilience and risk methodology. So where we really start from a very fundamental understanding of what actually poses threats or risks to infrastructure. How can we quantify that? How can we model that? What are the interdependencies of those risks? And how can we also, on a rather abstract level, model something like resilience, I mean, which is a big topic in itself and which has become a big buzzword, and also nowadays people are already rolling with their eyes if someone talks about resilience. But you can still think about this as something that can be quantified, at least something that can be quantified over time. And so we're really trying to do some quantitative research there, a lot of statistics, data science, technology that is going on there. And then what we do secondly is that, of course, if we want to monitor and improve the health status of infrastructures, then you have to detect certain things. You have to detect certain quantities of interest. You have to detect certain threats. You have to detect basically the current condition that your infrastructure is in. So you need very sophisticated sensors and sensor systems. And so we for this case, devoted an entire department of our institute to detection systems. So meaning that there we develop and we combine and fuse sensors into complex sensor systems. So going all the way also to mobile systems that you can deploy in crisis areas, like, of course, drones and mobile sensing system. And then at the core of what we do, as I mentioned now several times, is that we see a digital twin, and I'm going to come back later to that. We see the digital twin as kind of our core technology to do the things that we want to do. So meaning that we see a digital twin or digital twins as a kind of platform where we build from different inputs, where we build useful services, tools for prediction, tools for real-time monitoring, and so on. So we devoted another department to this topic of digital twins, where we really do the entire implementation from a software back-end point of view all the way to also software front-end, because at the end users will need something like a dashboard. I mean, probably you know all about this, but I'm still saying it again. It's like a dashboard where you can like have an overview of the current status of your infrastructure, and where you can make decisions, where you can play through what-if scenarios and do some simulations, etc., etc. And so the last small group that I added in recent years, because we saw that we have to invest there more, and this is kind of for me was the building the link to my previous research life, is that we said, well, we have to focus more on getting both high fidelity and reduced order simulation methods into the digital twin platform. So that's the topic of the last department that we have, meaning that I mean, I think a few years ago, some people advocated the idea that the big era of maybe simulation and mathematical modeling and computer modeling might be over, because now we just have data everywhere, and we just put this data into some kind of machine learning tool, and we press enter, and then we get all the predictions, all the information that we need. I think this kind of naive thought and honeymoon phase is also a bit over. Because we see that especially in engineering, and if you look about infrastructure, I personally feel that, and I always tell this, that I think that we don't have big data in the field of infrastructure, right? We have lots of data, but not big data in the sense of that classical deep learning techniques will just work as they do for distinguishing images of cats and dogs, for example, right? So we need to enrich the sensor data that we have with physics-based knowledge, and the best source for this is all the experience and all the knowledge that we've gained over years in mathematical modeling, in numerical methods, in simulation methods for all kinds of phenomena that show up in critical infrastructure. So this is the overall setup and theme. And so now I talked about this a lot, but I think it not only shows the organizational structure of our institute, so that was not my goal to show you how we structured our institute, but basically it also shows our approach and also our research philosophy to this field of critical infrastructure protection. And so I think this is one of the things that is also interesting for you, and I'm happy to discuss also this general philosophy. So now let's start more with the topic of the talk. So probably to this audience, I don't have to motivate too much that critical infrastructures are omnipresent and that their protection is of utmost importance for stable operation of all the critical services in society, and basically all the way to national and European security. And but still, I brought at least two spotlights to start off. So these are two of the images that I like to show, because they also show kind of some of the recent like mainstream media reports that you can see about such activities, at least in Germany. So the first one is a case from Germany. You might have heard about this one, or maybe not, because maybe it didn't reach out too far across Germany, abroad from Germany. So in September last year, basically a bridge running train tracks running over the river Elbe in the city of Dresden in eastern part of Germany collapsed really spontaneously, suddenly at night. So people were lucky. No one was injured or harmed, because it was at 3 at night and no one was passing over the bridge at that time. But it brought back this discussion about how to protect and how to monitor actually critical infrastructure that, of course, aging in Germany, just like in any other country. We have these aging infrastructures that have been around for decades and that will be around for some more decades. How to actually protect those, and it has fueled further this public discussion about the importance of critical infrastructure protection. And so the second one, just to contrast this a little bit, is an aerial view, a satellite image of the so-called Kachovka Dam, which is a big man-made dam in southern Ukraine. which has been, well, it's not fully clarified actually what happened, but there's some clear military tactical considerations that need to be taken into account. So it's quite obvious that the Russian forces obviously were interested in sabotaging this dam and basically bombing it or applying some kind of explosives. So actually what happened is that the dam flooded large parts of southern Ukraine. That happened in June 2023, which besides the whole of course catastrophic effects this had on the infrastructure there, also of course goes into the field of now security and military advantages and tactics. And so why I'm showing this is that I think now in Europe these days, maybe we still kind of resist the thought of, well, that we have to think about stuff like that. But in the field of critical infrastructure protection, actually, you cannot really draw a line between civil security on the one hand, that of course we all are aware of, and then also military considerations on the other hand. So I'm also advocating this, also being a member, of course, of a university of the German Federal Armed Forces. But also beyond, I'm advocating that we think more about civil-military partnership and also civil-military collaboration all across Europe, because basically those topics cannot be distinguished anymore, right? So nowadays there's drones every day, drones that we don't know about flying above critical infrastructure in Germany, and it's quite obvious who would be interested in monitoring and surveilling and maybe finding some things out about these infrastructures. So really, it's a topic that comes from, of course, a purely civilian application, but it's tightly connected these days also with military operations, and all the methods that we develop in this field and all the concepts that we develop. I mean, they are applicable to military infrastructure just in the same way as they are applicable to civil infrastructure. All right, so I'm gonna jump over this the first part now here a bit quicker, because I understand that you're all members of a master's program that focuses on critical infrastructure and digital twins. So probably I don't have to motivate now this too much. So obviously, as I already mentioned, we have different sectors of critical infrastructure that need to be safeguarded against threats, starting with energy sectors and transportation and traffic sectors, which are of course very obvious, going to water supply, IT, communication technology, all the way to healthcare, which has become very obvious during the pandemic, but also sometimes people forget about this, also like state and public administration, right? I mean, the state and all the important public functions must remain operable in a crisis situation. So it's critical in the very meaning of the sense that also such sectors are safeguarded, just like finance and other parts. And then the natural question that arises, if we talk about protection of infrastructure, we have to ask, well, protection against what? And again, this question is of course, the answer to this question is extremely broad. And so it showcases also the complexity of this research field and the diversity of this research field, because obviously, at the end of the day, and this is also a very common misconception, if you want to protect a certain infrastructure, let's think about some, I don't know, a nuclear power plant somewhere in France. There won't be, at the end of the day, again, that's my opinion, there won't be at the end of the day this one magic digital twin model in someone's computer that you just have to run and that will automatically safeguard and give you some information about all possible scenarios, about all possible threats, because they are just so diverse. So I also advocate a lot the view that we have to do in a first step a threat and risk analysis. So we have to analyze on what types of dangers and what types of threats we want to focus on. And then also we need to develop, and we also need to modularize some kind of problem-specific monitoring tools, some problem-specific digital twin that can answer relevant questions in that field. So a classical threat scenario, of course, that is somehow forgotten sometimes these days, but I showed it, I think, also with this bridge collapsing in Dresden, is this technical failure and lifetime issue, right? So I think this is by far the largest and most important issue that we have with all the among all the threats and dangers that are posed to our critical infrastructure. Because what most of the European countries, actually the entire Western world, have in common is that our infrastructure has been mostly built decades ago. In Germany, we have thousands of, for example, railway tracks, bridges in the railway system that are more than 100 years old, and they are still in full operation. So we have every day running hundreds of high-speed trains over those bridges, and we need to think about, so what is their status, right? And so we need to improve our knowledge and our mechanisms there. Nowadays, people are thinking more about, of course, due to climate change, extreme weather events, natural disasters. So this has become more and more important and more in the focus of the public, also in Germany. I mean, in some years ago in Germany, there's been this catastrophic flooding in West Germany in the so-called Ahr Valley. So Ahr is a small river in the west of Germany. And since then, it has basically reached the highest levels of political attention. But still, we're just the beginning. So one has to say that for many decades, these topics have just really been neglected to a very large extent. And then, of course, nowadays, people tend to think mostly about, if we talk about critical infrastructure, about sabotage, terrorism, hybrid attacks. So somewhere almost between some kind of warfare tactics. Of course, this is true, and this has emerged as an additional threat. But you have to see it in the correct perspective, right? So this is by far not I think personally is not the only and not the most imminent threat that is out there. But we have all these problems that we have to deal with first and foremost, which is related due to lifetime of our infrastructures. And I also think we shouldn't forget about extreme weather events and climate change. So to sum this up, what we are trying to do with all research activities in the field is that we or the people that I work with, because we're all basically mathematicians, natural scientists, computer scientists, engineers. So we try to develop new technologies that are somehow useful at the end of the day, right? For operating infrastructures, for safeguarding infrastructures, and so on. And so again, there's many different fields, I think, where you can excel in this mega topic of infrastructure protection, with the ones that are shown here just being some examples, like development of sensor technologies, and then also something like that people often forget. I think that at the end of the day, we need to convey our results of our methodologies to some users and decision makers, right? So often in crisis situations, we have some crisis teams, or even some on the political level, some decision makers. So we also need to make the results of our tools easily understandable. So that's why I also added here, for example, augmented and virtual reality. And I'm going to show an example later on how we try to do that within our research. But for me, of course, from the background where I come from, two of the main technologies that we need in setting up those hybrid digital twins, as we call them, is that we include methods and knowledge from mathematical modeling, numerical simulation. So that is the representative for the field of computational mechanics, and on the other hand, data science and scientific machine learning techniques. So I'm going to focus on that mostly when I show now some applications and some methods that we develop within our groups. So just one more information on what we do in terms of big projects. So I was very impressed when I heard and read after meeting Jeremy, when I heard and read about this very interesting research consortium here that you've put together. So on a much smaller scale, we're doing also something like that since a few years at my home university. So we have a project there that's called RISK.twin. So I mentioned it right at the beginning, where we really start from bottom up in a bottom up fashion. So where we select certain specific infrastructures where we have domain experts. So, for example, we've chosen bridges and then also water treatment systems as some of the example applications, and where we really in a bottom up fashion try to build up some useful digital twin, some digital twin platforms improving, for example, maintenance of such structures. And as I show later, what we do in the German Aerospace Center is more like a top-down approach, where we really try to set up and develop and push forward a more general concept of how to build such digital twins for any arbitrary infrastructure. So just to show you two examples from the RISK.twin project. Bottom up means that, probably you also know this, if you want to develop some maintenance, some monitoring tools for critical infrastructure, it's really important to get to the operator, right? So to have the operators on board. I mean, I'm just a scientist, right? So I need to work with some real life data at some point, and it's sometimes very, very difficult to convince operators of real infrastructure to share their data with, because that's basically their holy grail of what they have, and they're often hesitant to share that with you if you've not worked with them for like the last 20 years or so. So what we did there is that we tried to build up our own test facilities. So on the left you see a fully functional wastewater treatment plant. Okay, so we built this on our campus. So it's fully functional. It resembles, it's basically a small scale version of a water treatment as you see them in all your communities and all your cities, just on a smaller scale, but already beyond the lab scale, right? So you have to be realistic. So it's somewhere in between lab scale and real life scale. And why do we do this? Because with this, we can now operate this as a critical infrastructure, but we have full control over this. So we can, for example, deliberately introduce some crisis scenarios, some malfunctions, some extreme use cases up to a certain extent. I mean, we don't want to destroy our research infrastructure, right? But this has proven to be a very, very effective means, because then we can use this real life generated data right from the beginning to develop our tools, to improve our methods. And this has proven to be really, really important, because otherwise, if you work with some like manufactured use cases from the very beginning, where you don't have some real life connection, this will be very hard to come up with something that has meaning then later on in practice. And the same thing we do, you see a second image on the right, for wind turbines. So for wind turbines, I mean, one very important use case is, of course, to get a reasonable estimation of whether structural damage is happening in the blades, because like stopping the wind turbine and then doing some examination and some maintenance, of course, very costly. And so you want to have a very good real-time monitoring of what happens and some damage classification. But the problem is, of course, that it's really almost impossible to introduce all the sensors that you need for this into the structure to measure, for example, cracks. I mean, you would need some very, very delicate strain measurements, maybe with fiber optics. So you can't, or you don't want to do that. So what we do there is that we work with people from ETH Zurich, and they also have a spin-off company where they developed basically, you can think about it like a sock or like a sleeve that you pull over parts of the blade of the wind turbine, and that does aerodynamic pressure measurement. So we don't measure anything for the structural mechanics, but we actually only measure the aerodynamic pressure distribution around the airfoil, around the profile of the blade. And what we do then is that we apply some machine learning techniques to do some damage classification based on the aerodynamic pressure measurement. And we've shown in some preliminary study that we've published recently that you can also really get this information on potential structural damage, so on cracks that happen, for example, close to the foot of the blade, solely based on those aerodynamic pressure measurements, which of course would be very nice if we can now really translate this also into practice. All right, so some more theoretical words on what is a digital twin for us and how do we deal with this. So I know that this is really dangerous. I mean, going into this discussion of what is a digital twin, this can lead to like hours and hours of discussion. And so at this point now, I'm happy that we don't have this direct feedback, but you can also, of course, ask me later about it. So I don't want to go into the full scale into that discussion. So I'm just gonna show here a minimal definition that I think we all can agree on, hopefully, is that for me, a digital twin is a platform of some models that consists of a physical asset. So we have the real infrastructure, its digital counterpart, whatever that might be, with some bidirectional coupling. Okay, so we have the real infrastructure, we have some digital model or whatsoever, can also just be a data model or some digital representation, and we have coupling between those two. And this coupling needs to be bidirectional. So I think this qualifies as a digital twin. I mean, there's also recently been in the US this National Academies report led by Karen Wilcox and others. So I think it's very close to a minimal definition of this. And on the right-hand side, you can see that one like illustration that we came up with for having a more detailed concept for this, for specifically for critical infrastructure. So I just want to guide you very quickly through this, so that obviously we have the real world assets or the infrastructure, you have some virtual replicas, so the digital part of the twin, and then you have these connections that typical like in engineering, acting and sensing, right? So this is what I mean with bidirectional coupling. You need to be able to get some data through sensors from the real life system to the digital counterpart. And we need to be able, and this is sometimes forgotten, or maybe also forgotten on purpose, that you need to have some possibility of doing a feedback into the real structure, right? So whatever you do with your, for example, simulations or monitoring, you have to have a possibility to interact with the real life system, to change something in the real life system, like it's been for ages in control systems, right? So you have to have this feedback possibility. Otherwise, and now this is where the big discussion starts, it probably just qualify as a digital shadow or something like that. I mean, there's many of those definitions, but for the digital twin, you would need this bidirectional coupling possibility, at least. So the virtual replica is basically the digital model. So it represents the actual system state. And now that's where we specify this concept a little bit. It's the basis for doing virtual clones. Now the clone is again something else than the twin. So think of it as you have a digital model of your infrastructure, and now you create like 100 copies because you don't want to do simulations on the digital model, but you create some copies and you do some simulations, you play some scenarios. So that's what we call virtual clones of the systems. Then we have some toolbox. Obviously, that's where all our methods are implemented. So you want to do some, for example, I don't know, damage estimation, some maintenance scheduling, whatsoever. So these are all the useful things that you want to expect, that you want your digital twin to be able to do. And at the end of the day, you need some interaction also with the user. You need some dashboard. We call this control center. And so this is our general setup as we see it. And now I know this slide is, of course, now very high level and very future vision oriented, but still this is something that I also like to show, obviously also to potential partners and customers, is I think it's important that there's not this one size fits all or this one very complex overall digital twin of an infrastructure. I think this is a really common misconception. If you think about large airport or something like that, I believe that you won't have at the end of the day this one larger and larger digital twin model of this airport that tells you everything. So I think it's more like, you have kind of a modular structure in your software backend. So you have, for example, certain modules where you can do simulations. You could be, if we stay with the airport, right, you could do passenger flow simulation. That's one module. You could do like the simulation of how the aircraft move and operate on the airport grounds. You could have a simulation module for I don't know, for water systems at the airport, for the transport system, for the baggage of the passengers, and so on. So it's all modular. I need to bring that into one backend. The same for forecasting, right? So you can have different forecasting possibilities. All is modular. And now what should happen is that a new customer or user will approach you, right? So maybe now there's going to be the I don't know, French National Railway Agency approaching you and saying, well, now we want you to set up a model for the French TGV high-speed train system, and we want you to forecast on what are the most critical sectors in terms of extreme weather event whatsoever. And so our vision is that we now could develop out of those modules and put together an application-specific digital twin that then really provides useful services. And along the concept that maybe you are familiar with of software as a service, this would then be something like a digital twin as a service. And I think this is more the direction where this could develop in the long term. But of course, this is now just a very high-level idea, as I said earlier. Okay, so some just snapshots, images of projects where we're doing something like that. I will then show in just a minute. I will show one example in much more detail. So, for example, we're currently running large projects. You can see on the top left for increasing resilience of coastal regions. So this is basically motivated in Germany by climate change and more frequent extreme weather events. You might know that Germany has quite a long coastline with the Baltic Sea, but that's not so critical, but also with the Northern Sea. And so there it's very critical that you can have like severe floodings, then flooding entire coastal regions. And this is also very important because at this very same coastline, we also have large parts of our future energy infrastructure. So, for example, Germany has invested a lot in recent years to build LNG terminals. So for having a more stable gas infrastructure coming. So the big ships bring the natural gas via ships to Germany. So this needs to be protected there. So you have all these interdependencies between the systems. And so there's large efforts in analyzing those effects. A main focus of these projects is what we call cascading effects. So where you have interdependencies between different infrastructure sectors, and we want to come up with like in sensitivity analysis, if you're more like into maybe engineering sciences, you try to analyze which are the most critical connections, what could happen in certain scenarios. So we work a lot with like Bayesian decision theory and like Bayesian trees to model those interdependencies. On the lower left, you can see another scenario that is related to flooding. So this is more in an urban context now. So I think if I understand correctly, we're also focusing a lot on digital twins for not only infrastructure, but also city, like urban environments. So again, there what we do there is that we try to combine in a kind of multimodal manner simulation data from several domains, meaning that on the one hand we combine weather data with then also the availability of emergency services. So our customer at this point are something like firefighters, fire agencies that need to know where to deploy their units and also which hospitals that you can see maybe in this small image. So the small red crosses are basically locations of hospitals in the city area. So which hospitals are still reachable if we have this flooding scenario, which aren't. So this is basically the scenarios that then the customers are interested in at that point. And on the lower right, you can see something like a virtual reality environment. So in this case, it's really for training of emergency services, emergency fighters. So because an obvious problem is that, for example, firefighters, for good reasons, they cannot practice their critical crisis scenarios too often, right? Because luckily they do not, there's not a fire very regularly, right? Or not something going on very regularly. So one field of research that we are going is into setting up VR environments for training of emergency services, right? So where they can do some virtual training. And the picture on the top right I will show later on. So I'm gonna just mention this very quickly and focus on the second use case. So one use case that we are dealing with quite a lot but that goes really deep into civil engineering. So maybe it's a bit too specialized for you. Is bridge monitoring. So I just want to show some highlights from our projects there. So again, from this RISK.twin project, we were very lucky and very happy that we could actually build up what we call a real world laboratory. So what is a real world laboratory? So actually, you can see on the top left. So this is a really nice, typical small village in the south of Germany, right? And due to some personal connections, we were able to partner with them. They built a new bridge of the main road going through that village, which is not too far from Munich. And we partnered up with them, and we could integrate everything we could ever wish for having a full-scale infrastructure monitoring. So basically, we installed this bridge with over 150 sensor systems, so including really state-of-the-art fiber optical sensors that go along the reinforcement bars. So we can do now, since a bit more than 1 year, where this bridge was opened, we have a flow of real-time data coming into our servers, and we can use this, as I said earlier on, as a real life use case for developing then our methods. And we are quite proud about this because, I mean, you always have to be careful with this if you say you're the first in doing something, but we double checked. So this is, at least in Europe, the first fully digital bridge right from the opening to traffic. So meaning that it's a new bridge, and from day one, we have all the data, which is very critical and very important, right? Because often you have bridges that have already been around for like some time, but here, like right from the construction phase, we have all the data that we need. So this is also now for us some kind of test bed and a development test bed for developing further our methods. Okay, and this is all connected to this, so I'm just gonna jump over this. And I'm going to use the remaining time to focus on, well, one use case that maybe is not, well, let's see. So it's not maybe the most obvious use case if we talk about critical infrastructure, but it's related to that. And I like that use case very much, actually, because it showcases very nicely what we can do with digital twins. And also it has turned out to be very relevant, and we have many partners already for parts of this research, both on the emergency service level, but also on the critical infrastructure operator level. So the use case is a chemical accident. We come up with that use case basically with an industry partner that we have. So it's a large German company, Henkel, that I don't know how well known or not well known this is outside of Germany, but it's one of the largest chemical companies in Germany, and they operate one of the largest industrial facilities, so where they produce like chemical base substances in very close to the city of Düsseldorf. So Düsseldorf is a major city in Germany with around 500,000 or 600,000 inhabitants, and of course this company has been around for a while. And so this chemical plant that you can see in the satellite image on the top left is now very, very close. One might say too close to, of course, inhabited regions of the city, because the city has been growing, and basically it's now right in the city, right? So there's areas around it where people live and have their houses. So the use case that we obviously think about here is that some hazardous substance is released from part of their plant. So a hazardous gas phase substance, a hazardous gas. So that's one very realistic use case. What could, in the worst case, happen with them? So either due to some accident, right? But also, I mean, the reason could also be some terrorist sabotage act, right? So if you think about these drones that I mentioned at the beginning, that are now constantly flying across infrastructures in Germany. I mean, I don't know if you apply a certain amount of explosives to one of their drones or let it crash on the right spot. So this could also be the trigger for this use case. So anyway, so in short, the company and of course we from a research perspective are interested in what's going to happen in the case of a chemical accident. Of course, the problem that you have here, I mean, here you can see just some snapshot images. The problem that you have is that, of course, you don't know. So how will you actually learn about this chemical accident? Well, you will have some sensor systems deployed somewhere on your ground. So somewhere along this big chemical plant, which stretches over more than a square kilometer in this case. And so the question really is, so at some point, some sensor will be triggered and tell you, well, there's some hazardous gas flying around in a certain concentration. So you don't even know in the first place where the gas has been coming from. So in terms of now doing simulations or what a digital twin can tell you, you're of course interested in what we call a forward problem in mechanics. So where is the hazardous substance transported, right? That's what we want to know. And we want to know this fast, because this might be very important to tell people to evacuate, right? Because they shouldn't stay there. But the problem, as I mentioned, is that typically we don't even know, or we cannot model this forward problem or solve this forward problem appropriately, because for this, because it's a forward problem, you would need to know the initial conditions, right? You would need to know, where did this hazardous substance come from? Where did it start and when? And then we can do a forward simulation. So instead, what we have to focus on in these cases is that we have to solve so-called inverse problems, right? That also, you know, if you're in mathematical modeling and so on, you know about inverse problems, right? So first of all, we need to identify where is the source, right? We have to do source identification. Where has the substance actually emerged from? And we need to be able to do that with very little measurement data, right? Because of course you can always say, well, I need to, like, on this 1 square kilometer, like every 10 meters in a grid in both directions, I need to install a sensor. But this, of course, you cannot do, right? Because then you need to install hundreds and thousands of sensors, and it doesn't make sense. So you need to deal with the fact that you only have very limited measurement data, probably. And so this leads to automatically the second important question in terms of inverse problems, is where do you want to have new sensors maybe installed or additional sensors installed to secure certain areas. And the areas that you might want to secure most are, for example, something like assembly points or evacuation areas, like designated evacuation areas. So this is also the question that the customer might ask us. So where should I even install those sensors so that I have a maximum information gain? Then also you can do, of course, within a crisis scenario, you can do data assimilation. So you can have, it's depicted by this little drone here. You can have additional mobile sensor systems that you can deploy, for example, on a drone, to increase your level of information. So the question here would be, how could you route a drone? How can you do drone routing to improve the quality of your simulations, so that you would do in real time? You would send that drone off, and the data that the drone then collects, in addition to the stationary sensors, would then be used to improve your predictions. And at the end of the day, you can, of course, also solve then some optimization problems. So, for example, you could say, well, if people need to be evacuated, what is the safest evacuation route, for example, towards an assembly point? And I will show with some very simple example that there's also some interdependencies here. So in terms of the simulation part here, but I don't want to bore you with all the details. Obviously, we have to deal with what we call an offline and online phase, right? Because everyone who's done numerical simulation knows, of course, that high fidelity simulation is something that is not possible and will never be possible in real time. And in most of those scenarios, more or less, the prerequisite is that we are able to do, of course, predictions in real time. So in this specific scenario, it's about the dispersion of a gas. We need to have a very heavy offline phase where we do, for example, CFDs, or computational fluid dynamics flow simulations around this built environment in an offline phase, and where we then set up and we build some reduced order models that can then be used in the crisis case. So in the online phase, that can then be used, because they're then real-time capable, or maybe almost real-time capable, to then be used in the crisis scenario. In the crisis scenario, you just measure current environmental conditions, right? and we would then go step by step through this process. We would have to first compute where is actually the source location. We can compute then with this reduced order model the forward problem, so we can compute where's this gas transported. We can plan evacuation parts, and we can then, as you can see with this fighter fire with the iPad, we can then forward this information to the emergency service, and they can use it in guiding, for example, people towards safe areas. And obviously, this has to be done then, of course, also for 3D problems with very complex built environments. So the more complex and the more realistic this gets, and if you guys or some of you guys are then working on city scale simulation, this, of course, becomes very, very computationally heavy. And so the offline phase is something that needs to be planned very well and that I'm not going to address too much today. So just some images to show you.
Sorry to cut you, Alexander, but it's already like 53. If
sorry.
you can accelerate a little.
Almost done. Almost done.
Yeah, to still have some time for questions. Thank you.
Perfect. Almost done. So to just show you one or two exemplary images of what can be done there, I'm going to show you this, and then I'm going to go right to the conclusion. So what you can see here is just a small academic use case of a built environment. So these white parts that you can see are basically the footprint of certain buildings. And what you can now then see, if I run the animation, what you can see in black, with this black core, is the distribution of some hazardous substance. So that's the evolution of the gas transport. And what you can see in blue is, for example, is now a crowd flow simulation. So that would be the natural evacuation path of people. And you would see that it goes or cuts directly through this dangerous area going towards this green meeting point. So what we do then in these simulations is that we couple those two simulation modules, right? So that you say, well, the evacuation is guided by some guided evacuation helpers that avoids in real time to lead those people that need to be evacuated through a dangerous region, but that instead then guides them towards the spot on a different evacuation route so that no harm is done to those people to be evacuated. And also, of course, for the simulation of the forward problem, I'm going to skip this. So this is really the last thing that I'm going to show, because this shows how we integrate at the end of the day all this into technology. So we call this a situational awareness table. It's a virtual reality application that we invented. So at this, you can see in this virtual reality environment, first of all, the built environment. In this case, it's the chemical plant. And now you can really do everything that I talked about, these forward simulations, inverse problems, in a crisis scenario in real time on this VR table. So why in VR? Because we often have the situation that crisis teams cannot be assembled fast enough, right? So these people are just sitting somewhere in their offices so they need to meet online and in a virtual room, because this is the fastest possible way. And they can have like an online crisis meeting and now do some simulations, some what if scenarios, and check. So where do I have to deploy the firefighters? Where do I have to evacuate? And to make those decisions in real time and assisted by those digital twins. So with this, sorry for taking a bit too much of your time, but I hope that I gave a bit of an overview of what we're trying to do here. And so I'd be very happy to continue those discussions with whoever's interested. And thank you very much for your attention, and happy to interact more.
Thank you. Thank you.
Yeah, thanks a lot. Sorry again to rush you, Alexander. Just quick question, by the way. Can you provide us the PowerPoint?
Yes, I can. I will have a quick. Yes, I will have a quick check, and I might have to
but confidentiality,
2 or 3
of course.
images.
Yes.
But apart from that, it's going to be just fine.
Yeah, perfect.
Of course.
Thank you.
Yes.
Thank you.
Sure.
If anyone has any question, please, you can either unmute yourself, or if you don't want to, just type in the chat. So, is there any question? So maybe I will start with the first one. So, as you mentioned, you are dealing with risk and critical infrastructure